Take control of the end-to-end data lifecycle. Thank you for taking the time to attend today's enablement session. My name is Gopal Raghavan, and I'm part of Cloudera's partner programs and strategy team. I'll be covering the different customer data lifecycles as part of our enablement. We will go over why managing these data lifecycles is important for enterprises that are looking to get a competitive edge in their respective industries. What does data lifecycle mean for our customers? If you ask our customers in the telcos, financial, airlines, oil and gas, manufacturing, and automotive sectors, they'll tell you they want different types of analytics for their diverse user base to implement mission critical use cases, all managed by a central security, metadata, and governance layer. In other words, a data lifecycle to them provides multifunction analytics at each stage within the data journey, integrated with the centralized security and governance layer. So what does this data lifecycle look like? Data lifecycle starts with a collect phase. In this phase, data ingest, ETL, integration teams collect data from different systems across all infrastructures, whether cloud, in the data center, within the edge, and send that to the data lake. Once in the data lake at rest, the curation phase starts. Here, the data engineering teams take the data and put it in a normalized view that can be consumed by downstream systems. In the next phase, reporting, typically BI analysts run queries or dashboards against these structures. An example is data warehouse optimization use cases. The next phase, serve, a subset of the data is served up to real-time applications. Here, the use cases are operational data warehousing, research and discovery, etc. In the final phase, the data scientists tap into the data to build and train models. Here, machine learning engineers and machine learning operations take those models and productionalize them. Within each of these phases, CDP provides an analytical experience. For the collect phase, we have streaming and data flow. For curate, we have data engineering. For reporting, we have data warehousing. For serve, we have operational DB. For predict, we have ML and AI with Cloudera machine learning. Each of these experiences is connected via SDX, which provides the security and governance layer. Let's make this data lifecycle a bit more real. Healthcare costs in the US have been rising at an alarming rate, so much so that they make up 17% of our annual GDP. One of the biggest issues influencing healthcare cost is fraud. Large healthcare insurance companies are exposed to hundreds of millions of dollars per year in fraudulent claims. To recoup these losses, they turn to recovery agents who can cost up to 1/3 of the recovered amount. So in a typical year, it is expected to cost them over $100 million. This is analogous to debt collectors hired by banks and other financial institutions when customers default on loans. It is costly for the bank to repossess the car, sell it, pay off part of the debt, and continue collecting if there is unpaid debt. Ideally, loans are not given to customers that are going to default to avoid the expensive collection or repossession process. So to avoid paying for the recovery agents who cost well over $100 million, they want to detect fraudulent claims before there's ever a payment. To do that, they want to develop a process to flag potential fraudulent claims for further analysis by their own agents before paying claims. So what does the data lifecycle look for this customer's fraudulent claims use case? A high-level pipeline is illustrated here. As a first step, claims data arrives on a daily basis. They need to read and clean the raw data from the landing zone, enrich it by combining it with data from external systems like customer profiles in their MDM systems. These curated data sets are then used to build and train the machine learning models. These models are then productionalized to assign a fraudulent score. The customer agents in the serve phase then query for the flag claims to determine if the claims are fraudulent or not. CDP provides an analytical experience for each phase of the data lifecycle. Cloudera data flow, or CDF, for data collection of the claims. Cloudera data engineering, or CDE, for cleaning, optimizing, and enriching data. Cloudera machine learning, or CML, for the data scientists to build and train models which are used to flag the fraudulent claims. Cloudera data warehouse, or CDW, for the agents to review and query the fraudulent claims. The shared data experience, or SDX, then enables the shared security and governance for this entire data lifecycle pipeline. What you're looking at here is the lineage of the customer's fraud claims prediction model that is currently deployed in production. The questions they want to answer are, what is the audit trail to this model? What are the data sources and the processing done to lead to the creation, training, and deployment of this machine learning model? Let's break it down. We see Cloudera data flow consuming claims data from a set of queues doing some processing, converting the data from CSV to JSON, and then landing this data into two S3 buckets. We then see Cloudera data engineering, CDE, consuming this data from the S3 buckets and creating an external table. This data is parsed, enriched, and curated to create a Hive table called claims curated label. We then use Cloudera machine learning, or CML, to query these two Hive tables to create a machine learning model and expose it via REST endpoints. SDX uniquely captures this end-to-end pipeline from a security and governance perspective. If the customers want to be a data-driven organization and truly become a digital enterprise, it is mandatory for them to master this data lifecycle. However, the reality is the customers struggle to start this lifecycle journey. The first problem the customers encounter is the first mile problem, or lack of agile data collection tools. When we talk to platform or data ingestion teams, the problems of data source diversity and scalability comes up. For example, one of our customers who specializes in toy production onboards 10 different data sources weekly. Another customer, who is a massive telco company, expects the data collection to go up by 25 times when 5G is rolled out and is in use. When we talk to data or app developers, they often talk about agility, that it takes too much code to develop, maintain, and add new sources and their uniqueness. When we talk to CISO, VPs of platforms, they often bring up compliance requirements. For example, one of our retail customers used a homegrown ingestion tool built in Java for the last 20 years. These tools don't meet the compliance requirements of Sarbanes-Oxley, CCPA, GDPR, etc. So how do we solve this first mile problem? This past year, we delivered flow and edge management solutions aimed squarely at solving the first mile problem. They provide a canvas with drag and drop components to build complex data pipelines without writing a single line of code. Out of the box, they provide 300 plus pre-built processors to ingest data from any source that an enterprise requires to perform filtering, routing, enriching data, and delivering those streams to downstream systems. These aim to solve agility, data source diversity, scalability, and compliance issues we've seen in earlier sections. What are the use cases that our customers use flow and edge management offerings for? There are two categories. The first category is data acquisitions. Examples include inside edge data collection. One of our large oil and gas customers deploy Minify agents on thousands of their Windows machines to replace their Splunk forwarders. Another oil and gas customer deploys Minify agents on hundreds of gas stations to collect logs for analysis. The third example is an airline customer who deploys Minify agents on their kiosks for proactive maintenance. You will hear about this use case later in the later sections. Another example includes log collection and ingestion at extreme scales. As an example, one of our large telco customers will collect 5G network logs, among others, using flow management powered by Apache NiFi. This means 25 times volume over what is currently being collected, which is enormous to begin with. The second category of use cases is intelligent data movement. Examples include replacing a legacy data movement tool written in Java at one of our retail customers, moving HL7 data from EMR systems via Cloudera data flow for advanced analytics, and a large customer that built an intercontinental data exchange to move data between USA and India. In the process of moving this data, they want to filter, enrich, and redact information based on legal and compliance rules. The data lifecycle we saw in the earlier section only represents part of the data lifecycle journey. More and more customers require real-time insights. One of our champions at a large insurance company, who is a VP of architecture, summed it up the best. We can't wait for data to persist and run jobs later. We need real-time insights as the data flows through our pipeline. In other words, no one wants to wait till all the data is persisted overnight before trying to drive insights from it. There is little gain and a great deal of loss in slowing down the movement of data. So if you look at the traditional data life cycle, after the collect phase, we are landing the data, putting it at rest before curating, reporting, serving, and then building predictions of it. This traditional data life cycle has some innate challenges. In talking to the VPs and directors of engineering, they often talk about the challenges of building event-driven applications using legacy technologies. For example, up-and-coming fintech companies are able to implement push notifications for wire transfers quite easily, whereas the legacy players are finding it tough to do so with their technology debt in legacy systems. When we talk to enterprise app architects, they talk about challenges of meeting low latency process requirements. For example, a major financial player experienced a massive outage a few years ago as they were not able to handle 30 million monthly active users. When we talk to VPs or directors of IoT or cyber, they talk about not only detecting threats in real time, but also acting on them. Use cases such as these are difficult to handle if you wait for data to be landed. At some point in time, the information gets really stale. So let's look at how we can address these challenges. With the traditional data life cycle, we talked about how the multifunction analytics of curating, reporting, serving, and predicting occur after the data has landed. The other part of the data lifecycle is to perform these multifunction analytics while the data is in motion or transit, in other words, within the stream itself. This starts with buffering the streams in real time. This is performed by streams messaging powered by Apache Kafka. By buffering these streams, we allow applications to subscribe to these streams in real time. These streams are then used by these applications for processing. In the next phase, we distribute these streams to downstream systems for processing. This is done by flow management powered by Apache NiFi. In this phase, we can filter, process, and normalize these streams for downstream processing and analytics. In the next phase, we can do analytics and complex event processing within these streams. This is performed by streaming analytics powered by Apache Flink and Spark structured streaming. In the last phase, we can act on insights derived within the streams in real time. The key value proposition is these two data life cycles are intrinsically connected to each other. For example, we can take the buffered streams and send it to data lake for batch curation. We can distribute the streams, and while distributing, we can enrich the streams from data lake for reporting purposes. In the analyze phase, we can deliver the insights from the stream and serve it up to the serving layer for real-time, low-latency applications. Finally, we can take the model we built, and instead of using the model to score in batch, we can score in real time within the streams. Let's make the data lifecycle a bit more real. Let's take the example of an airline's customer. They want to be able to know in real time if a kiosk was going to run out of paper and act on it before it does. For this customer, being able to answer this question affects the customer experience and in turn, its bottom line. This either results in happy customers or angry customers. Let us see what the data lifecycle looks like for this particular customer. Let's start with the collection phase. Streaming events at every kiosk are collected and sent to the buffer. The buffer phase allows apps to subscribe to the streaming events in the collect phase. In the distribute phase, we tap into the streaming events to parse, enrich, filter, and distribute the streams. For example, the data from the events contain complex nested JSON. We simplify the structure in the distribute phase to ensure that these streams can be processed by downstream applications. In the analyze phase, a real-time application which subscribes to these events is designed to detect event patterns. In this example, the app detects that the kiosk is running out of paper, or if more than 80 of the 120 kiosks are in service. Based on the insights generated, we can act in real time. For example, notify an airline agent that the paper needs to be refilled or have technicians deployed to take care of the problem. It's worthwhile noting that this entire, for each phase of this data lifecycle, CDP provides an analytical experience. In the collect phase, Minify agents are deployed on the kiosks to capture these streaming events. In the buffer phase, we have streams messaging powered by Apache Kafka to buffer the streams in real time. In the distribute phase, we have flow management powered by Apache NiFi to parse, enrich, filter, and distribute these streams to downstream analytics. In the analyze phase, we have streaming analytics powered by Apache Flink to do complex event detection and processing. It is worthwhile noting that this entire lifecycle happens in the stream, and at no time does data come to rest. This complete and connected data lifecycle introduces a third use case: real-time, low-latency streaming analytics. For example, one financial customer is building push notifications using Apache Kafka and Apache NiFi. For another financial customer, they're using Apache Flink, Kafka, and NiFi to modernize their mobile banking systems for low-latency processing. For a medical equipment customer, they're able to, in real time, collect and process the cardiac data from the medical devices in patients. In an automotive customer, they are able to build real-time IoT streaming platforms for reading exhaust information. In an insurance customer, they're able to leverage streaming for speed-based insurance rates. We've used a lot of terminology like Minify, NiFi, Kafka, etc. in this presentation. Let's take a look at where and how these capabilities are used for data in motion use cases. It's a bit confusing as to what does what. So let's try to break it up as much as we can. Minify is used for edge data collection. For example, if you want to collect data from devices like watches, sensors, etc., Minify is used to do that. Kafka is used to build fault-tolerant publish and subscribe architectures. NiFi provides a canvas with processors that can be dragged and dropped to build zero-coding pipelines for moving data. Flink is a processing engine for surfacing insights from data. In addition to Flink, there are additional processing engines like Kafka Streams and Spark Structured Streaming in the platform. In the next section, we'll see how they differ from each other. Spark is a way to microbatch in seconds. So there are no features to do complex analysis. And if you truly want real time, then this may not be the viable engine for your use case. Kafka Streams provides millisecond latency. It is very simple, but it is limited to Kafka. It does not do complex analytics processing. Flink is the ultimate solution which provides millisecond latencies and complex analytics processing. For example, if you want to see how many users were on a system in 5, 10, 15-minute intervals, that's a type of time windowing analysis. Flink can help you with that. Additionally, if you want to know, for example, how many times a user X was logged in a 24-hour period, that's windowing. Flink can support these types of use cases in millisecond latencies. Now let's take a look at a use case which illustrates how one of our customers, a large financial institutions, use capabilities from our platform to take control of their lifecycle to meet SLAs. This customer was struggling to modernize their capabilities to be current with the latest customer requirements. They accumulated quite a bit of technology debt from their acquisitions. Additionally, they suffered an outage which affected their mobile app as well as their website for several hours. They also ran into significant legal and compliance issues a few years ago. The two key folks that were tasked to lead the modernization efforts were the EVP of Digital and SVP of Engineering Strategy. Their main goal was to ensure that they were able to deliver a 99.99% uptime SLAs to their active users. The fact that they had legacy Hortonworks awareness from a previous experience, along with knowledge of streaming, helped quite a bit in the modernization journey with CDFs. Their current workflow is as follows, and the current workflow is legacy workflows. Devices and apps connect to their CDN, which is their content delivery network. In the second step, this is then routed to the edge and in turn, their core networks. In the third step, there are custom applications that are on the core network that deal with the requests from devices and applications. In the fourth step, these are all routed, all the data requests are routed to SOR, which is system of record, and third-party data repository, like credit card vendors. And the system of record is a repository for all transactions like accounts. If you could see here, there's a lot of legacy applications cobbled together. Now, let's look at their future state. Request comes in from an external device like phones, browsers, etc. It gets routed through Kafka, and then a Flink consumer reads the Kafka queue and sends it to MongoDB. MongoDB then orchestrates the information which is sent back to Flink. Flink aggregates all of that and serves it up via Kafka, which is routed back to the source. So this is you can see there's quite a bit of improvement as compared to their legacy workflows. Now, what is the lesson learned from here? So the world is changing. There is a massive shift to streaming-based analysis. You have to look for enterprises that have needs for real-time, low latency, complex event processing use cases. But the pain points are these people have enormous legacy debt. So they're struggling to innovate, but they can't because of technology debt. You have to look for the streaming team or the digital or customer experience owner. They are the ones really looking to solve their pain points. And you rest assured that we have the best streaming solution in the market. So be very confident and diagram the data lifecycle with your customer to help them visualize. So far, we have talked about the traditional data lifecycle and where data is at rest. We have talked about the first mile problems and mastering that first mile to start the data lifecycle. We have talked about the complete data lifecycle where both data at rest and data in motion work together to solve the streaming real-time use cases. Now, let's take a look at the last mile problem. The last mile problem is productionalizing machine learning models. An IDC study says only 35% are reporting getting machine learning capabilities into production. This means people are spending lots of money and data science teams are building these really cool things that never leave the walls of the lab. There is something that's causing this issue, and Gartner called it the wall to production, the barrier to getting these machine learning capabilities embedded and maintained in a real business process once you have built the model. Why is that? Why are we not seeing that ROI? So there is a people and process aspect. The machine learning capability development cycle is not like the traditional software development cycle. You can't use waterfall method. You can't really use traditional agile. End-to-end machine learning requires collaboration across business stakeholders, IT, and data science teams. It's an iterative, cyclical team sport. It starts off with obtaining business inputs and requirements. Data engineering curates the data scientists build and train the models, IT DevOps packages the models, and machine learning ops and engineering deploy and score the model in batch or streaming. Business is constantly monitoring the accuracy of these models, which drives decision making. As you can see, operationalizing machine learning models needs coordination between multiple groups and require access to the entire data lifecycle. And why is it so hard from a technology standpoint of view? As we have seen from the previous slides, in addition to coordinating between different groups of people and functions, we also have to think about managing the data and its security and governance context throughout the lifecycle. Silos are the enemy of AI-powered progress. Developing and putting machine learning capabilities to work for business requires more than machine learning tools and capabilities. It requires end-to-end data and analytics pipelines. Because CDP provides a complete and connected DLC with experiences at each stage within that lifecycle, and SDX provides a shared security, metadata, and governance layer, it becomes easy to deploy these models at any given point in the lifecycle. Hence, the complete data lifecycle, access to the data across the lifecycle, analytical experiences for each part, removes the barrier to productionalizing these machine learning models. Now, here are the key takeaways. Let's summarize the key pain points. The first mile problem deals with a lack of agile data collection tools to onboard newer and more varied data sources. This results in a lot of missed business opportunities. For a lot of enterprises, a traditional data lifecycle, which deals with data at rest, is not sufficient. They are looking to modernize these capabilities to onboard use cases with streaming data to get a competitive edge in their respective industries. The last mile problem deals with the ability to productionalize machine learning models. This prevents a business from maximizing the value of its data assets. Cloudera's data platform capabilities enable customers to get control of their data across the entire data and analytics lifecycle. Other vendors like point solutions support some functionality, but not all. Their offerings are not integrated to work easily together, so they perpetuate data and organizational silos. A connected data lifecycle is critical to meet the needs of real-time use cases. Cloudera is the only solution capable of addressing this critical requirement for enterprises who are struggling to maximize the value of their most precious asset, which is data. Focus on use cases that correspond to the three problem categories. Examples of some of the use cases include IoT for the first mile problems, quality monitoring, which requires harnessing or streaming data, is an example of where customers are challenged with just the data at rest lifecycle. And finally, smart cities, which require an H2AI comprehensive set of capabilities all the way from data collection to productionalizing machine learning models for prescriptive decision making. Thank you for taking the time to attend this session. See you in the next.